Welcome to the AMD Vivado ChipScope Analyzer Hardware Debug for FPGA and Adaptive SoCs Tech Module. Here's the agenda for this tech module. We will focus on ChipScope components, debug flows, and ChipScopy. After successfully implementing your design, the next step is to run it in hardware by programming the FPGA or Adaptive SoC and debugging the design in system. There are four main debug steps. They are probing, implementing, analyzing, and fixing. Probing. Identify the signals in your design that you want to probe and how you want to probe them. Implementing. Implement the design that includes the additional debug IP attached to the probe nets. Analyzing. Interact with the debug IP contained in the design to debug and verify functional issues. Fixing. Fix any bugs and repeat as necessary. AMD provides a ChipScope debug solution, which reduces the time required for verification and debugging. The ChipScope provides a comprehensive flow to maximize visibility into programmable logic for design debug during system operation. It accesses Vivado Logic Analyzer VLA, which is a Vivado front-end dashboard that interacts with debug cores in your design. It uses the debug cores for triggering and data collection without consuming any I/O pins, as data is captured through the device JTAG pins. It supports various triggering scenarios, allows flexible, targeted probing, and configures most debug parameters at runtime, ensuring adaptability. Additionally, captured data can be reused as test vectors and test benches, enhancing design verification. A single JTAG connection simplifies both programming and hardware debugging. The Vivado ChipScope is comprised of two basic items: debug cores that sample and inject signals into the programmable logic to enable design visibility without obstructing design functionality. These debug cores include the Integrated Logic Analyzer (ILA), System ILA, Virtual Input Output (VIO), JTAG to AXI Master, etc. Debug cables for either standard JTAG debugging and high-speed debug of heterogeneous systems. Probing flows for inserting these debug cores into the design and monitoring the signals marked for debug. These include the HDL instantiation and netlist insertion flows. The Customizable Integrated Logic Analyzer ILAIP core is a logic analyzer core that can be used to monitor the internal signals of a design. The ILA core includes many advanced features of modern logic analyzers, including Boolean trigger equations and edge transition triggers. The Vivado Design Suite provides an ILA core wizard for the designer to enter all the parameters for the ILA core, such as component name, number of probe ports, sample data depth, and trigger and storage settings. The ILA debug core consists of up to 1,024 user configurable probe ports, eliminating the need for external user input or output for triggering, data capture, and communication. The signals in the design are connected to the ILA probe and slot inputs and are sampled at design speeds and stored using on-chip block RAM. The probe, sample, and trigger functionality is implemented in the programmable logic region. No user input or output is required to trigger events, capture data, or to communicate with the ILA core. ILA core is capable of monitoring interface-level signals. It can convey transaction-level information, such as the outstanding transactions for AXI4 interfaces. The communication with the ILA core is conducted using an auto-instantiated debug core hub. The Vivado IP catalog also offers a system ILA IP core which can be used to monitor the internal signals and interfaces of a design. The Virtual Input Output VIO core is a customizable debug core that can both monitor and drive internal signals in real time. It inserts virtual pins into the design and can produce up to 65 input and output probes, with each port width is customizable up to 256 bits wide. Unlike the ILA core, no on-chip or off-chip RAM is required. It presents and captures data on the design clock attached to the clock input port to the sampled data. The inputs and outputs can be visualized in different ways, as virtual LEDs, push button, or toggle switches added at the last minute to an FPGA design. The JTAG to AXI master debug feature is used to generate AXI transactions that interact with various AXI full and AXI Lite slave cores in a system that is running in hardware. The core supports all memory-mapped AXI and AXI Lite interfaces and can support 32 or 64-bit wide data interfaces. We recommend using this core to generate AXI transactions and debug drive AXI signals internal to an FPGA or adaptive SoC at runtime. The BSCAN to JTAG converter core bridges the gap between BSCAN and JTAG interfaces, offering compatibility for designs where the debug interface supports JTAG but not BSCAN. This IP converts BSCAN signals into JTAG signals, enabling seamless JTAG transactions. It is compatible with the Vivado IP integrator and can be instantiated in HDL designs. The core facilitates writing and reading data through the JTAG interface, with data written to the BSCAN interface generating corresponding JTAG transactions. It is particularly useful for applications that support JTAG input but lack BSCAN support. With no internal buffering, the core ensures transactions occur without delay. Let's explore the various data cables used for programming and debugging, along with their features and target applications. The platform cable USB 2 is a general-purpose cable primarily used for programming and debugging. It supports a wide range of devices, including UltraScale, 7 Series, Vertex, Spartan, and Zynq 7000 SoCs. This cable operates with target clock speeds ranging from 750 kHz to 24 MHz. It uses USB 2.0 for connectivity. Debugging features include JTAG, slave serial, and SPI programming. It is powered through a USB port and offers FPGA-based acceleration while maintaining backward compatibility with the platform cable USB. The SmartLink data also focuses on general-purpose programming and debugging. It supports devices from UltraScale, UltraScale Plus, 7 Series, Zynq 7000 SoCs, and more. This cable provides JTAG rates of up to 40 megabits per second and connects via both Ethernet and USB. Key debugging features include JTAG debugging and indirect flash programming. It can be powered through USB or Ethernet and includes GPIO ports for additional functionality. Before diving into the SmartLink Plus, let's discuss the High-Speed Debug Port, or HSDP. HSDP provides a unified, high-bandwidth debug and trace interface. It enables at-speed system trace capabilities across various blocks in Versal devices, such as the programmable logic, processing system, and AI engines. Additionally, HSDP supports debugging and configuring multiple devices in a system. Its high-speed GT-based interfaces, like the integrated Aurora interface in the PS block or the PCIe interface in the CPM block, ensure efficient functionality. Now, moving on to SmartLink Plus. This is designed specifically for high-speed debugging and tracing in Versal adaptive SoCs. It offers exceptional trace capture speeds up to 10 gigabits per second, making it 100 times faster than standard JTAG. Connectivity is provided through the High-Speed Debug Port, HSDP. Unlike the previous options, it includes up to 14 gigabytes of trace memory for enhanced debugging capabilities. Additional features include high-speed trace, smart filtering, a programmable debugger, multi-user support, and compatibility with heterogeneous architectures. However, It requires an external power source and is optimized specifically for Versal adaptive SoCs. There are two Vivado logic analyzer probing flows that are available in the Vivado IDE. First is the HDL instantiation flow. This flow involves the manual customization, instantiation, and connection of various debug core components directly in the HDL design source. The IP catalog from the project manager is used to locate, select, and customize the desired debug cores, such as ILA VIO and JTAG to AXI. This requires modifying the HDL code to instantiate the cores in the design, necessitating a rerun of synthesis, implementation, and bitstream generation. This flow allows probing at the HDL design level only. The second is the netlist insertion flow. This flow is limited inserting an ILA core. A simple wizard creates and configures ILA cores automatically based on the selected nets to debug. This flow inserts the core directly into the netlist, eliminating the need for design resynthesis. It is generally easier to add and remove debug cores using this method. Moreover, the netlist insertion flow allows for probing at various design levels, such as HDL, synthesized design, and system design. The Vivado tool automatically inserts the ILA core into the post-synthesis netlist, enabling you to select the nodes of interest from the synthesized design. This approach requires only implementation and bitstream generation after core insertion. The Vivado design suite also allows the designer to mix the HDL instantiation and netlist insertion flows. Regardless of how the cores are inserted into the design, after the final netlist is generated, the rest of the flow is identical to a non-logic analyzer flow through the implementation tools and bitstream generation. The Vivado hardware manager is used to download the bitstream to the FPGA, and the logic analyzer can then be used to interact with the debug cores in the FPGA. The HDL instantiation probing flow involves the manual customization, instantiation, and connection of various debug core components directly in the HDL design source. Adding the debug cores in the design using the HDL instantiation flow involves different steps. Step 1. Generate and customize debug cores. Open the Vivado IP catalog and navigate to Debug and Verification. Debug to locate the supported debug IPs, including the Integrated Logic Analyzer, ILA, JTAG to AXI Master, and Virtual Input-Output, VIO. Customize a debug core by double-clicking it or right-clicking and selecting Customize IP. In the customization window, assign a component name and configure settings like probe port count and width for ILA or VIO cores. After customization, generate the debug core IP to add an .xci source file to the project. Step 2. Instantiate debug cores. Switch to the IP Sources tab in the Sources window to locate the generated debug core. Ensure the output products, such as instantiation templates, synthesis, and simulation files, are available. Open the .veo or .vho instantiation template. For VHDL designs, copy and paste the component declaration and instantiation into the VHDL source file. For Verilog designs, copy and paste the instantiation into the Verilog source file. Replace the instance and net port names to connect signals to probe for debugging. Step 3. Synthesize and implement. Run synthesis from the Flow Navigator in Vivado to integrate the debug cores into the design. After synthesis, open the synthesized design to verify the debug cores in the debug window. Debug cores are automatically connected to the debug hub core, which appears as a black box. Properties of debug cores can be updated using the Properties window. The netlist insertion flow is a method for adding debug cores, specifically the ILA core, to your design after the synthesis stage. Step 1. Mark debug signals. The first step in the debugging process is to identify and mark the signals of interest for debugging. This can be achieved by adding the mark debug attribute directly to the desired signals in the HDL source code, or by specifying the signals in the XDC constraint file. Step 2. Set up Debug Wizard to insert debug cores. The Setup Debug Wizard in Vivado automates the creation and configuration of ILA cores, simplifying the process of connecting marked debug signals to the core inputs. The wizard pre-populates the list of debug nets, allowing users to add or remove nets using the Find Nets to Add option or the plus and minus icons. It also supports net filtering and name-based searches for precise signal selection. Marked signals are assigned to the ILA core inputs, and for signals crossing multiple clock domains, users can manually override the default selection and choose the desired clock domain to ensure accurate data capture. Core parameters, such as trigger conditions and probe types, for example, data, trigger, or both, are configured during this step. Once the configuration is complete, the wizard inserts the ILA cores into the post-synthesis net list, and a summary confirms the number of cores added and their associated clock domains. Step 3. Implementing debug cores. Debug core implementation is integrated into the standard implementation flow, which includes place and route and bitstream generation. During this process, the debug cores are synthesized as black box instances, and their net lists are automatically added to the project. These cores are included in all implementation runs, with their connectivity preserved through netlist updates. When debugging designs, fast debug methodologies play a critical role in accelerating the process while preserving implementation results. The incremental compile flow allows you to modify debug cores while reusing 95% of the prior placement and routing results. It is ideal for significant debug modifications, such as adding, deleting, or altering debug cores, including their parameters like probes or data depth. This flow operates on a synthesized design or a design checkpoint DCP with a reference design. While it requires partial reimplementation, it speeds up place and route using prior results, making it time efficient as long as the design retains at least 95% similarity. The eco flow focuses on replacing existing debug nets with minimal changes, ensuring previous implementation results are preserved. Unlike the incremental compile flow, the eco flow is applied to already implemented design checkpoints. It is best suited for minimal and non-invasive debug changes, such as replacing debug nets connected to the ILA core. By avoiding full reimplementation and rerouting, this flow saves valuable time while ensuring minimal impact on the overall design. The comparison table highlights the differences between the eco flow and the incremental compile flow. Chipscopy stands for Chipscope Python. This package provides a simple Python interface to program and debug Versal devices. Chipscopy APIs have a 100% Python code base, which is free and open source on github.com. It is a standalone installation, which means the Vivado tool is not required to use it. Chipscopy is an open source project that enables high-level control of the Versal debug IPs in the design. Using these Python APIs, developers can control and communicate with debug IP cores such as the ILA, VIO, device memory access, and more. Chipscopy is currently only supported for Versal devices. Chipscopy allows you to access the hardware over many interfaces such as JTAG, PCIe, Ethernet, or Aurora, HSDP, for device detection, programming, and status. It also allows you to create your own Python script using any Python IDE, like Jupyter Notebook, which communicates through the APIs. Here is a list of resources for getting started with Chipscopy APIs. Also available are various Chipscopy getting started videos.